Picture our sun as it is today, steady, golden, almost boring in its reliability. Now wind the clock back 4.5 billion years. The same star is a monster. It is swollen far larger than it is now, blotched with dark magnetic bruises bigger than entire planets, hurling flares thousands of times more violent than anything we see today. And here is the strange part. While it swallows a river of gas spiraling inward, it simultaneously fires twin jets of matter out into the dark at hundreds of kilometers per second. It is feeding and screaming at once. This is no fantasy. It is the violent infancy of stars like our own, a stage called the T Tauri phase. Tonight, you will see why young stars rage. Before we go further, if you find this kind of slow, deep wander through the cosmos fascinating, a quick like or subscribe genuinely helps this channel keep growing. It only takes a second for you, but it means a lot to me. Now, let's begin. There is a star you have seen every single day of your life, and you have never once thought of it as dangerous. It rises in the morning, it crosses the sky, it sets in the evening, and it does all of this with the patience of something that has been doing the same thing for billions of years. Our sun is steady, it is reliable, it is, in the most literal sense, the calmest important thing in your life. You can set a clock by it. You can plant crops around it. You can build an entire civilization on the quiet assumption that tomorrow it will do exactly what it did today. But that calm is a kind of lie. Or rather, it is the end of a very long story whose beginning was anything but calm. Because 4.5 billion years ago, before there was an Earth to stand on, before there was a single ocean or a single breath of air, the object that would become our sun was not a peaceful golden disk. It was a raging, swollen, magnetically tortured young star, far larger than the sun you know, blotched with dark spots the size of worlds, throwing flares so violent they would dwarf anything our modern sun has produced in all of recorded history. And while it did all of this, it was performing a trick that sounds almost impossible. It was pulling matter inward and flinging matter outward at the very same time. This violent infancy has a name. We call stars in this stage T Tauri stars, and tonight we are going to understand exactly what they are and why their youth is so furious. We are not going to start at the very beginning, in the cold darkness of a collapsing cloud, because by the time our story opens, a recognizable young star has already formed, and a disk of gas and dust already surrounds it. Instead, we begin at the strangest and most overlooked time in any sun-like star's life. The time after it has been born, but long before it has settled down. The awkward, explosive adolescence of a star. So let us begin with the most important question. What exactly is a T Tauri star? The simplest answer is that a T Tauri star is a young, low-mass star that has emerged from its hidden birth, but has not yet grown up. To understand why that matters, you have to understand that stars, like people, pass through distinct stages of life, and the personality of a star changes dramatically depending on which stage it is in. There is the buried, embedded beginning, when the future star is still wrapped in the thick cocoon of gas and dust from which it formed, glowing mostly in infrared, invisible to ordinary eyes. That earliest stage is the protostar, and then at the far end, there is the long, stable, productive middle age, the phase our sun is in right now, where the star quietly fuses hydrogen in its core for billions of years and asks almost nothing of the universe except to be left alone. The T Tauri stage sits in between these two. It is the bridge. It is what happens after the star has shrugged off most of its birth cocoon and become a distinct, recognizable object you could point a telescope at. But before it has reached that quiet, hydrogen-burning maturity, it is the years between leaving the womb and finally standing on solid ground. And like most in-between stages, it is messy, loud, and full of energy that has nowhere settled to go. Now, when astronomers say these stars are low mass, they mean something specific. A T Tauri star is generally less than about 2 times the mass of our Sun, and very often around the Sun's mass or below. These are not the giants of the cosmos. They are not the rare, blazing heavyweights that burn out in a few million years and explode. They are ordinary, modest stars, the kind the galaxy makes by the billions, the kind that will eventually live calm and enormously long lives. The violence we are about to explore does not come from these stars being huge or exotic. It comes from them being young. That is one of the most important ideas in this entire story, so hold on to it. The fury of a T Tauri star is not the fury of a monster. It is the fury of a newborn that has not yet learned to be still. To place this stage properly, imagine the full road a star like the Sun travels. It begins inside a cold molecular cloud, a vast region of gas and dust drifting in space. A piece of that cloud collapses under its own gravity, growing hotter and denser at the center, until a glowing core forms deep inside the murk. That core, still buried, still gathering material, is the protostar. Over time, the infold slows, the surrounding envelope thins, and the young star begins to peek out from its veil. The moment it becomes visible as a distinct star, still surrounded by a flattened disk of leftover material, still nowhere near stable, is the moment it enters the T Tauri stage. And from there, over millions of years, it slowly tightens, slowly heats its core, slowly approaches the conditions it needs to begin its real adult life. When it finally crosses that threshold and settles into stable, self-regulated hydrogen fusion, it joins what astronomers call the main sequence, and the T Tauri chapter closes forever. Astronomers have a way of charting this entire journey, a kind of map on which a star's life can be traced, and it helps to know it exists because it is how we know where the T Tauri stage truly sits. If you plot stars according to how bright they are and how hot their surfaces are, they do not scatter randomly across the chart. They fall into distinct regions, and a star's position on this map tells you what stage of life it is in. This chart, one of the most important tools in all of astronomy, is called the Hertzsprung-Russell diagram, and on it, the long stable main sequence forms a clear band where mature stars like our Sun reside. A young T Tauri star does not sit on that band. It sits above and to the side of where it will eventually settle, in the region reserved for stars that have not yet reached maturity. And here's the beautiful part. Because the star is contracting and slowly changing as it ages, it does not stay in one spot on the chart. It traces a path across it, a track that carries it over millions of years from its swollen youthful position down toward the main sequence band where it will finally come to rest. We can, in effect, watch a star walk toward adulthood along a predictable route, and a T Tauri star is a star somewhere along that walk, still on the road, not yet arrived. This is also why T Tauri stars are not scattered evenly across the sky, but cluster in particular places, and knowing where to look tells us something about them. Because these stars are young, they have not had time to drift far from where they were born. and they are found gathered in and around the great clouds of gas and dust that serve as the galaxy's stellar nurseries. The Taurus Auriga complex, where T Tauri itself resides, is one such nursery, one of the nearest and most studied to Earth, lying a few hundred light-years away and rich with young stars at every stage of their early lives. But it is not the only one. Other nearby star-forming regions hold their own populations of young stars, their own crowds of T Tauri objects glowing within the clouds. A single nursery can hold dozens or hundreds of young stars at once, born together from the same parent cloud, now strewn through its glowing remains like sparks scattered from a common fire. A T Tauri star found alone in the empty dark, far from any cloud, would be a strange thing indeed. They belong to the nurseries, gathered where stars are born, and that gathering is itself a sign of their youth. So the T Tauri stage is the unstable transition. It is the climb. It is the period after birth and before maturity, and everything strange about these stars flows from the fact that they are caught between two very different ways of being a star. This brings us to a point that is easy to get wrong, and it is the single most important physical fact about a T Tauri star. So let us be very careful with it. A T Tauri star is not yet powered in any dominant or stable way by the fusion of hydrogen in its core. That sentence deserves to be taken in twice, because it overturns the simple story most of us carry in our heads, the story that says a star is just a ball of gas-burning hydrogen. That description is true of our sun today. It is true of the main sequence, but it is not yet true of a T Tauri star, the great regulated furnace that will one day run for billions of years has not yet switched on as the star's primary engine. The core is hot, but it is not hot enough, or not stably hot enough, to make hydrogen fusion the steady heart of the star. And yet, a T Tauri star shines. Often it shines more brightly than the sun does now. So if it is not running on the fusion of hydrogen, where does all that light come from? The answer is one of the most beautiful ideas in all of stellar physics, and it is the key that unlocks everything else. A T Tauri star shines, in large part, by falling. Not falling through space, but falling inward on itself. The star is slowly, relentlessly shrinking, contracting under its own gravity, and that contraction releases energy. This is the mechanism known as gravitational contraction, sometimes called Kelvin-Helmholtz contraction after the physicist who first understood it. When any object collapses inward under gravity, it converts the energy of that infall into heat. A young star is, in effect, an enormous ball of gas that is forever falling into itself, and the heat from that endless inward squeeze leaks out from its surface as light. Think about what that means. The light pouring off a young T Tauri star is, to a large degree, the light of gravity at work. It is the glow of a star paying its own weight inward, gram by gram, layer by layer, releasing warmth as it tightens. The star is not yet earning its keep through the fusion that will sustain it for the rest of its life. Instead, it is living off the energy of its own collapse, like a person living off savings before they have start their real job. And just as savings run down, this energy source is temporary. Gravitational contraction can power a star for millions of years, but not for billions. Eventually, the squeezing drives the core hot enough that true hydrogen fusion ignites and takes over, and the contraction halts. But during the T Tauri stage, the star is still in that earlier phase, still shining on the borrowed light of its own slow fall. Once you understand this, a strange and wonderful consequence falls into place, and it explains one of the most counterintuitive facts about young stars. A T Tauri star is usually larger and brighter than the mature star it will eventually become, even though it has exactly the same amount of material. Take a young star with the mass of our Sun. You might assume it looks more or less like the Sun. It does not. It is puffed up, swollen, bloated to a size noticeably greater than the Sun's, sometimes several times the Sun's radius. And because it is so much larger, with so much more glowing surface, it can pour out far more light than the Sun does today, even while running on nothing but gravity. This is the opposite of what intuition suggests. We tend to imagine that things grow into their final size, that young means small. But a star works the other way around. It begins large and diffuse and contracts toward its mature, compact form. The young star is big precisely because it has not yet finished shrinking. Over the millions of years of the T Tauri stage, it gradually pulls itself in, growing smaller and, in some ways, dimmer, marching steadily toward the tight, stable body it will be for the rest of its life. So, when you picture a young version of the Sun, do not picture a smaller Sun. Picture a swollen, oversized one, brighter and more bloated than the calm star we know, slowly deflating across millions of years toward maturity. But size and brightness are only part of the story. The truly defining feature of a T Tauri star, the thing that first made astronomers notice them at all, is that they refuse to hold still. Their brightness flickers and jumps in ways that are irregular and unpredictable. A mature star like our Sun is a model of consistency. Its output barely changes from year to year, decade to decade. A T Tauri star, by contrast, can brighten and dim on timescales of hours, days, or weeks, with no neat repeating rhythm you can rely on. It is restless. It is moody. It changes its mind. And much of this variability has nothing to do with the gravitational contraction we have been discussing. It comes from the violent surface activity and the steady rain of infalling matter that we will explore a little further on. For now, simply hold the picture in your mind. A young star is not just larger and brighter than its future self. It is also wildly more variable, a flickering, unsteady light where the mature star will one day burn smooth and constant. So we now have a portrait taking shape. A T Tauri star is a young, low-mass, pre-main sequence star. It sits in the long transition between the buried protostar and the settled, hydrogen-burning adult. It has not yet made stable core fusion its primary engine. It shines instead, in large part, on the energy of its own gravitational contraction. It is bigger and brighter and far more variable than the mature star it is destined to become. It is, in short, a star in the middle of growing up, and like all growing things, it is awkward, oversized, and impossible to predict. Now, where did this strange name come from? And how did we ever discover that stars pass through such a phase? For that, we need to travel to a particular patch of sky and meet the star that gave the entire class its name. High in the northern winter sky lies the constellation Taurus, the Bull, one of the oldest constellations recognized by humanity, marked by the glittering cluster of the Pleiades and the orange eye of the bright star Aldebaran. Within Taurus, far dimmer and far less famous, sits a faint, unremarkable-looking point of light that you would never notice with the naked eye. It is called simply T Tauri. The name follows an old astronomical convention for labeling variable stars in a constellation, and the letter at the front is part of that catalogue system. But that humble designation, T Tauri, would go on to name an entire category of stars across the galaxy, because this faint flickering point turned out to be the prototype, the first well-studied example of a star in this violent young phase. T Tauri lies roughly 470 light years from Earth, which means the light you would gather from it tonight in a telescope left that star centuries ago, long before anyone understood what they were looking at. And for a long time, no one did understand it. What astronomers noticed first, going back well over a century, was simply that this star would not stay put. Its brightness wandered. It flickered and changed in ways that ordinary stable stars did not. It was lumped in with other oddball variable stars, its true nature a mystery. The breakthrough came in the middle of the 20th century. Observatory logbooks recorded its wanderings year after year, brightening here, dimming there, in a pattern no astronomer could fit to any known rule. And so it sat among the unsolved curiosities of the sky, waiting for someone to recognize what its restlessness truly meant. In 1945, an astronomer named Alfred Joy carefully studied T Tauri along with a handful of similar restless stars and realized they shared a whole family of peculiar traits. They were all variable in that irregular, unpredictable way. They all showed certain telltale features in their light that hinted at hot, turbulent activity and material moving rapidly around them. They were all found in or near clouds of gas and dust, the very regions where stars are born. Joy recognized that these were not random misfits. They were members of a single class, united by youth, and he named that class after its most prominent example. From that moment on, stars like these were T Tauri stars, and the faint flicker in the ball became the namesake for one of the most important stages in stellar life. What made T Tauri the perfect prototype is that almost everything strange about young stars is on display in it. It is not a lone star, for one thing, but part of a small multiple system, with companions tangled up in the same youthful chaos. It sits within the Great Taurus star-forming region, sometimes called the Taurus-Auriga complex, one of the nearest and most heavily studied stellar nurseries to Earth. This region is a sprawling network of cold gas and dust, dotted with young stars at various stages of their early lives, and it has become something like a natural laboratory for understanding how stars like our sun begin. When astronomers want to study stellar youth, this is one of the first places they turn, and T Tauri itself sits near a glowing patch of nebulosity, a faint cloud lit and shaped by the young star's restless energy. And here is the detail that ties this whole story back to you. T Tauri is not some alien object with nothing to do with our world. It is a low-mass star, much like the Sun in the basic ingredients of its construction. When we look at T Tauri and the other young stars scattered through the Taurus clouds, we are very likely looking at a living portrait of what our own Sun was like in its infancy. We cannot travel back 4.5 billion years to watch the young Sun directly, but we can do the next best thing. We can look across the galaxy at stars caught in the same stage right now, frozen for us in the act of growing up, and read in them the lost chapters of our own star's youth. Every flicker of T Tauri is, in a sense, a glimpse of a story that has already happened here, in our own corner of space, long before there was anyone to witness it. it is worth pausing to feel the strangeness of that. The sun that warms your face, the sun that has been a symbol of constancy and reliability in every human culture that ever lived, was once a wild, swollen, flickering thing, very much like that faint point in Taurus. The same star that now keeps perfect time was once unable to hold its brightness steady for a single week. The calm we take for granted was earned. It was the end of a turbulent adolescence that lasted millions of years, and the evidence for that adolescence is written across the sky in the young stars still living through it today. But we have only begun to answer the deepest question. We know now what a T Tauri star is. We know it is young, low in mass, caught between birth and maturity. We know it shines on gravitational contraction rather than on stable hydrogen fusion. We know it is larger, brighter, and more variable than the star it will become. We know it was first recognized in a faint flicker in the constellation of the Bull. But we have not yet explained the violence. We have not yet explained why this oversized, contracting young star is also covered in storms, racked by flares, and capable of throwing matter into space. The contraction we have discussed is slow and steady. It is not, by itself, dramatic. A star quietly shrinking and glowing with the warmth of its own collapse would be remarkable, but it would not be violent. So where does the fury come from? Why does a young, modest, sun-like star behave less like a peaceful furnace and more like a storm that never ends? The answer lies in everything we have not yet talked about. It lies in the disk of leftover gas and dust still wrapped around the young star. A disk that is not just sitting there passively, but is actively feeding the star, pouring material down onto its surface along invisible channels. It lies in the star's tangled, ferocious magnetic field, far stronger and far more chaotic than the magnetic field of our calm, modern sun. And it lies in the way these two things, the infalling disk and the magnetic field, collide and combine to produce hotspots, ultraviolet glare, monstrous flares, powerful winds, and those impossible twin jets that fire matter out into the dark, even as the star drinks matter in. The young star, in other words, is not violent simply because it is contracting. It is violent because it is still assembling itself, still exchanging matter and motion with the disk around it, still magnetically wild in a way that maturity will eventually tame. It is feeding and growing and spinning and storming all at once, and the result is one of the most energetic and dramatic phases any sun-like star will ever pass through. That is where we are headed next. We have met the young star and learned what it is. Now we have to watch it eat. Because to understand why these stars rage, we first have to understand the great river of matter falling inward, the disk that surrounds them, and the strange magnetic machinery that funnels that material down out of the dark and slams it onto the surface of a star that has not yet learned how to be still. We left the young star in the middle of a mystery. We had learned what it is, a swollen, contracting, flickering thing, shining on the borrowed light of its own collapse, caught in the long climb between birth and maturity. But we had not yet explained the violence. A star quietly shrinking under gravity is a gentle thing. It does not throw flares. It does not flicker wildly from one night to the next. It does not fire matter into space. So to understand the fury, we have to turn our attention away from the star itself for a moment and look at what surrounds it. Because the young star does not hang alone in empty space. It is wrapped in a vast, flattened, spinning disk of gas and dust, and that disk is the source of much of the drama to come. This disk has a name. We call it a protoplanetary disk, and the word itself contains a promise. Proto means first or earliest. Planetary tells you what the disk will eventually become. This is the raw material from which planets are made, the leftover gas and dust that did not fall all the way into the star during its birth. When a cloud collapses to form a star, it is almost never sitting still. It is always turning, however slightly, and the laws of physics demand that as it shrinks, that turning must speed up. The same way a spinning figure skater accelerates when she pulls her arms in. The collapsing cloud cannot funnel all of its material straight down onto the newborn star, because that spin flings much of it outward into a broad, rotating sheet. The result is a star at the center and a wide, thin disk of material wheeling around it, like a record turning around its spindle, or like the rings of a planet scaled up to enormous size. Picture it clearly, because the picture matters. At the center sits the young T Tauri star, oversized and glowing. Stretching out around it, lying flat in a plane, is the disk, made of gas, mostly hydrogen, mixed with fine dust grains, ices, and the heavier ingredients that will one day become rock and metal. This disk can stretch across distances many times the span between our sun and its outermost planets, reaching out tens or even hundreds of astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. This temperature gradient across the disk, hot near the star and frozen at the edges, is far more important than it first appears, because it divides the disk into 2 very different realms. Close to the star, where the disk is hot, it is too warm for ice to survive. Any water, any frozen gases are vaporized, kept in gaseous form by the heat, leaving only rock and metal able to remain solid. But travel outward, away from the star, and you eventually cross an invisible boundary where the temperature drops low enough that water freezes into solid ice and stays frozen. Astronomers call this boundary the snow line, and it is one of the most consequential features of any young disk. Inside the snow line, in the warm inner region, the solid material available to build worlds is limited to rock and metal, which is why the inner planets of a system tend to be small, dense, rocky bodies. Outside the snow line, in the cold outer region, ice joins rock and metal as a solid building material, dramatically increasing the amount of stuff available to assemble into planets, which is part of why the outer planets of a system can grow into giants. The same disk, then, holds the recipe for 2 utterly different kinds of world, divided by a line drawn in temperature, set by the heat of the young star at its center. And all of this is happening against a clock, because the disk does not endure. Observations of young stars across many star-forming regions reveal a consistent pattern. The thick, gas-rich inner disks that feed classical young stars typically survive only a few million years, often fading within something like 1 to 10 million years before the gas is largely gone. That may sound like an eternity, but in the life of a star that will shine for billions of years, it is the briefest flicker of an opening. Everything that must be built from gas, every giant planet's thick atmosphere, every world that needs to gather its envelope from the disk, must be assembled within that narrow window before the material vanishes. The young star, by feeding on its disk and blasting it with a radiation, is helping to close that window even as planets race to form inside it. The disk is both cradle and hourglass, nurturing worlds while steadily running out of time. It is hottest and brightest near the star, where the material is packed close and bathed in heat, and it grows colder and darker as it spreads outward into the dim, frozen reaches at its edge. Within this disk, over millions of years, dust grains will collide and stick. Pebbles will gather into boulders, boulders into mountains, and mountains into the cores of planets. Everything you know, every world in the solar system, begins as a swirl of material in a disk like this one. But tonight, the disk interests us for a different reason. It is not just a nursery for planets, it is a source of food for the star. And the way the star eats is one of the strangest and most important processes in all of stellar youth. You might imagine that material in the disk simply spirals lazily inward and gently settles onto the star's surface, like water swirling down a drain. The reality is far more violent and far more interesting, and it hinges on something we have not yet brought into the story. Something that turns the calm image of a feeding star into the picture of a star under bombardment. That something is the star's magnetic field. A young T Tauri star possesses a magnetic field of extraordinary strength and complexity, far more powerful than the field of our calm modern sun. We will dig into where that ferocious magnetism comes from in due course. For now, what matters is its effect on the disk. The magnetic field does not stay politely confined to the star. It reaches outward, threading through space, pushing against the inner edge of the disk. And here a kind of standoff takes place. Close to the star, the magnetic field is so strong that it overpowers the disk entirely, sweeping it clear, carving out a hole. The disk cannot survive right up against the star. The innermost region is swept empty by magnetic force, leaving a gap between the star's surface and the point where the disk truly begins. So the material in the disk cannot simply drift all the way down to the star along the flat plane. It reaches the inner edge of the disk, the edge of that swept clear hole, and there it runs into the wall of the magnetic field. And this is where the magic happens. The process that defines how a young star feeds. The process astronomers call magnetospheric accretion. The two halves of that phrase tell the whole story. Magnetospheric refers to the star's magnetic field, its magnetosphere. Accretion is the word for matter falling onto and joining an object, growing it, feeding it. Magnetospheric accretion, then, is the feeding of a star along the channels of its own magnetic field. Here is what actually unfolds. When the gas at the inner edge of the disk meets the powerful magnetic field, it becomes captured by it. The gas in these disks is not ordinary, neutral, inert material. It is partly ionized, meaning some of its atoms have been stripped of electrons and carry an electric charge, and charged matter is helpless against a strong magnetic field. It cannot cross the field lines freely. Instead, it's forced to move along them, like a bead threaded onto a wire, sliding wherever the wire leads. And the magnetic field lines, anchored in the star, arc up and out of the disk plane and curve down toward the star's surface, often toward regions near its magnetic poles. So the captured gas is lifted up out of the flat disk, hoisted onto these curving magnetic channels, and then it slides down them, falling along the field lines, raining down onto the star. Imagine standing at the inner edge of that disk and watching. The flat sheet of material reaches inward, and then, at a certain point, the gas lifts off the plane, peeling upward and inward, climbing onto invisible arcs of magnetic force. It flows along those arcs like water, flowing along curved pipes, accelerating as it goes, drawn down by the star's gravity, channeled by the star's magnetism. These streams of infalling gas are sometimes called accretion columns or funnels, and that is exactly what they are. funnels that carry disk material out of the plane and down onto the star in concentrated rivers rather than an even rain. The star is not being fed gently from all sides at once. It is being fed through a handful of focused channels, like a body fed through a few narrow tubes rather than bathed evenly in nourishment. And the speed of that infall is the key to the violence. The gas does not drift down, it falls. It is pulled by the gravity of the star across a real distance. And like anything falling under gravity, it accelerates. By the time it reaches the star's surface, it is moving at a tremendous velocity, a substantial fraction of what physicists call the free fall speed, the maximum speed an object reaches when it falls freely under a star's gravity. We are talking about gas slamming down at hundreds of kilometers per second. To put that in human terms, this is matter striking the star at speeds far beyond any rocket, far beyond any meteor entering Earth's atmosphere. A relentless, high-velocity bombardment, falling onto the surface through the magnetic funnels. Now ask yourself, what happens when something moving that fast hits a surface and stops? The answer is the same as what happens to a spacecraft slamming into the atmosphere or a hammer striking an anvil. The energy of motion has to go somewhere, and it converts into heat. When the infalling gas, screaming down the magnetic funnels at hundreds of kilometers per second, crashes onto the star's surface, it is abruptly halted, and all that energy of motion is released as a violent burst of heat and light at the point of impact. The gas does not land softly. It strikes, it shocks, and the spot where it lands flares up far hotter than the surrounding surface of the star. These blazing landing zones are called accretion hotspots, and they are one of the signature features of a feeding young star. Picture the surface of the T Tauri star, glowing at its own ordinary temperature, and then picture, in the regions near its magnetic poles where the funnels come down, intensely bright patches where infalling gas is hammering the surface. These hotspots are dramatically hotter than the rest of the star, sometimes burning at temperatures far above the surrounding surface, because they are not heated by the star's own internal warmth, but by the kinetic violence of the bombardment landing on them. They are bruises of light, places where the star is being struck so hard and so fast that it glows white hot in concentrated patches against its calmer face. And because these hotspots are so much hotter than the rest of the star, they pour out a particular kind of radiation in great excess. Hotter surfaces emit more of their light at shorter wavelengths, shifting toward the blue and beyond into the ultraviolet. So the accretion hotspots of a young T Tauri star blaze in ultraviolet light far more strongly than the star itself otherwise would. This is one of the fingerprints astronomers use to recognize a feeding young star. When they measure an excess of ultraviolet light, more than the star's own temperature could account for, they are seeing the glow of those impact zones, the radiation of disk material being slammed onto the surface. The star carries a kind of signature of its own feeding, written in ultraviolet, a glow that announces matter is still falling in. Now we can finally return to the great mystery we set up at the very beginning. The irregular flickering, the unpredictable changes in brightness that first made these stars famous and gave them their identity as variables. We can now see where much of that variability comes from, and it is a direct consequence of everything we have just described. Consider the situation. The star is being fed not evenly, but through a few concentrated funnels. The disk that supplies those funnels is not perfectly smooth and steady. It is clumpy, turbulent, uneven. Sometimes more material reaches the inner edge and pours down the channels in a surge. Sometimes less reaches it and the flow thins to a trickle. The rate of feeding rises and falls, gusting like wind, and as it does, the hotspots brighten and dim in response. When more gas hammers the surface, the hotspots flare brighter and the star's total light climbs. When the flow eases, the hotspots cool and fade, and the star dims. The star's brightness, in other words, is tied to its appetite, and its appetite is anything but steady. On top of this, there is the star's rotation. The young star spins, and as it turns, the hotspots, anchored to particular regions of its surface near the magnetic poles, are carried around with it. From our distant vantage point, a bright hotspot might rotate into view, brightening the star, and then rotate around to the far side, hidden from us, dimming it again. So the star can pulse simply because it is spinning, carrying its blazing patches in and out of our line of sight. Combine the gusting, uneven feeding with the turning of the star, and you get exactly what astronomers observe. Brightness that wanders and jumps on timescales of hours, days, and weeks, never settling into a perfectly clean and predictable rhythm. The flickering of a T Tauri star is, in large part, the flickering of a star being fed in fits and starts while it spins, its hotspots brightening, fading, and wheeling across its face. This is a profoundly different picture of a star than the one most of us carry. We think of a star as a fixed, steady light, unchanging, eternal. But a young T Tauri star is a dynamic, restless object, locked in an ongoing exchange with a disk around it. Drinking matter through magnetic channels, glowing with the heat of impact, brightening and dimming with every gust of its uneven meal. It is less like a candle and more like a fire being fed irregular handfuls of fuel, leaping and sinking as the fuel comes and goes. It is worth dwelling on the sheer scale and strangeness of what this means physically. The young star is reaching out across space with its magnetic field, grabbing material from the inner edge of a disk that may lie millions of kilometers away, lifting that material out of the disk plane and channeling it down onto itself in concentrated streams moving at hundreds of kilometers per second. The star is, in a very real sense, using magnetism as a set of arms to pull its food up out of a spinning plate and pour it into itself along a few narrow throats. No mature star does anything remotely like this. Our calm, modern sun has long since lost its disk and finished its feeding. It sits in splendid isolation, fusing hydrogen, asking nothing of the space around it. But the young star is still connected, still tethered to its disk by invisible magnetic threads, still in the middle of building itself from the material it was born with. This connection between star and disk is not a minor detail. It is in many ways the defining relationship of stellar youth, and it has consequences far beyond feeding. The magnetic link between the star and the disk also governs how fast the star spins, because as material flows down from the disk and joins the star, it carries motion with it. And the magnetic threads connecting star to disk act almost like a brake or a clutch, trading spin back and forth between the two. There is a delicate, ongoing negotiation playing out, with the star and the disk locked together magnetically, exchanging both matter and rotational motion across the gap between them, in a relationship astronomers describe with terms like corrotation, the region where the disk and the star turn in step. We will see a little further on how crucial this exchange of motion becomes, because it sits at the very heart of why these stars are able to throw matter outward, even as they pull it in. But the disk does more than feed and break the star. It also shields and shapes the entire young system, and it will not last forever. The protoplanetary disk is a temporary thing, a phase, just as the T Tauri stage itself is a phase. Over millions of years, the disk is steadily consumed. Some of its material rains down onto the star through the very accretion process we have been describing, slowly eaten away from the inside. Some of it gathers into planets, locking the dust and gas into worlds. Some of it is blasted away entirely by the star's radiation and winds, stripped from the system and lost to space. Bit by bit, the great spinning plate is emptied, and as the disk dwindles, the feeding slows, the hotspots fade, the flickering quiets, and the star drifts toward the calm, diskless maturity that awaits it. The end of the disk is, in a sense, the end of childhood, but that ending lies far ahead of us in the story, and there is a great deal of violence to witness before we reach it. For now, let us hold the picture we have built. The young star sits at the center of a vast, flattened, spinning disk of gas and dust, the raw material of future planets. The star's powerful magnetic field carves a hole in the inner disk and reaches out to capture the ionized gas at its edge. That captured gas is lifted out of the disk plane and funneled down along magnetic field lines, falling onto the star at hundreds of kilometers per second. Where it strikes, it creates blazing hot spots, far hotter than the surrounding surface, glowing in excess ultraviolet light, the signature of a star being fed. And because the feeding gusts and surges, and because the star spins and carries its hotspots in and out of view, the star's brightness flickers and wanders in the irregular way that first gave T Tauri stars their name. This is the inflow, the great river of matter falling in, the first half of the impossible double act we glimpsed at the very beginning. But we have been speaking again and again of the star's magnetic field as though it was simply a given, a tool the star happens to wield. We have watched it carve holes in disks, capture ionized gas, build funnels, and break the star's spin. We have treated it as the central machinery of stellar youth without ever asking the obvious question. Why does a young star possess such a ferocious magnetic field in the first place? Our calm modern sun has a magnetic field too, but it is mild by comparison, gentle enough that we mostly ignore it. The young star's magnetism is something else entirely. Stronger, wilder, more tangled, powerful enough to dominate an entire disk and reshape the flow of matter across millions of kilometers of space. And it is this same ferocious magnetism that does not merely feed the star, it also tears at it. It covers the young star in storms. It builds enormous dark spots across its face. It unleashes flares of staggering power, blasts of energetic particles, and floods of high-energy radiation. And, most astonishingly of all, it provides the engine for the great paradox we have been promising since the first words of this story. The way a young star can fling matter outward into space along its poles, even as it drinks matter inward at its equator. The funnels we have watched pouring material down onto the star are only one side of what this magnetism can do. The other side fires matter away from the star entirely, out into the dark, in narrow beams that punch across light years. To understand that, we have to go to the source. We have to ask where the wild magnetism of a young star is born, deep inside its churning, rapidly spinning, convecting interior. And we have to follow that magnetism upward, out of the star's depths, to its tortured surface and beyond, into the storms and flares and jets that make the youth of a sun-like star one of the most violent chapters it will ever know. That is where we turn next. We have been treating the young star's magnetic field as a kind of given, a tool it simply happens to wield. We've watched it carve a hole in the disk, capture ionized gas, build funnels of infalling matter, and slam that matter onto the surface in blazing hot spots. But we never stop to ask the obvious question, and it is time to ask it now. Why does a young star have such a savage magnetic field in the first place? Our calm modern sun has a magnetic field, yes, but a mild one, gentle enough that on most days we forget it is there. The young star's magnetism is a different beast entirely. Stronger, wilder, more tangled, powerful enough to dominate an entire disk and bend the flow of matter across millions of kilometers. To understand the violence of stellar youth, we have to find the source of that magnetism, and the source lies deep inside the star, in the churning, spinning fury of its interior. A magnetic field anywhere in the universe is generated by moving electric charge. In a star, that charge is carried by the hot, ionized gas of its interior, gas in which atoms have been stripped of electrons and now carry charge freely. When that charged gas moves, it generates magnetic fields, and when those fields in turn push the gas around, you get a self-sustaining engine, a loop in which motion makes magnetism and magnetism shapes motion. Physicists call this engine a dynamo. Every magnetically active star runs one. The question is not whether a star has a dynamo, but how powerful and how wild that dynamo is, and the answer depends almost entirely on two things: how the star's interior churns and how fast the star spins. On both counts, a young T Tauri star is built to produce magnetism of extraordinary ferocity. Start with the churning. The interior of a star is not still. Heat generated deep inside has to escape to the surface, and in much of a young, low-mass star, that heat is carried by convection, the same process you see in a pot of boiling water or a mug of heated soup. Hot material rises, cools near the surface, sinks back down, warms again, and rises once more in great rolling cells of circulation. A young T Tauri star is, through much or even all of its bulk, a churning, convecting body, a vast cauldron of rising and falling currents of ionized gas. And because that gas is charged, every one of those churning currents is also a current of electricity, a moving river of charge twisting and folding through the star. This deep, full-bodied convection is a magnetism-making machine of tremendous power. The whole star, in effect, is one enormous, turbulent dynamo, far more vigorously convective than the calm, layered interior of our mature sun, where convection is confined to a relatively thin outer shell. Now add the second ingredient, rotation. A young star spins fast, often far faster than our sun spins today. Remember where it came from, a collapsing cloud that had to speed up as it shrank, like the figure skater pulling in her arms. The newborn star inherited a great deal of that spin, and it has not yet had time to shed it. So the young T Tauri star turns rapidly on its axis, sometimes completing a rotation in a matter of days, where our mature sun takes nearly a month, and rapid rotation supercharges a dynamo. As the star spins, it drags its churning, charged interior around with it, twisting and stretching the magnetic fields, winding them up tighter and tighter, amplifying them, organizing the chaos of convection into something even more powerful. The combination of deep, vigorous convection and rapid rotation is the perfect recipe for a ferocious magnetic field, and that is exactly what a young star has. Its magnetism is born of the marriage between a churning interior and a fast spin, and the offspring of that marriage is a field of extraordinary strength and tangled complexity. It is worth slowing down to see exactly how rapid rotation turns an ordinary dynamo into a violent one, because the mechanism is both simple and beautiful. A star does not rotate as a single rigid body the way a solid ball would. Different parts of it turn at different rates, a behavior called differential rotation, with some regions completing a turn faster than others. Now picture a magnetic field line threaded through this rotating, churning gas. Because the gas is ionized and charged, the field line is effectively frozen into it, dragged wherever the gas goes. As different parts of the star sweep past one another at different speeds, they grab hold of the field lines running between them and stretch them, pulling them out, winding them around the star like thread being wound onto a spool. A field line that began as a simple arc gets stretched, wrapped, and amplified, its strength growing as it is wound tighter and tighter. Layer this stretching on top of the constant up and down churning of convection, which twists and braids the field lines further, and you have a recipe for magnetic chaos. The faster the star spins and the more vigorously it churns, the more violently the field lines are stretched and tangled, and the stronger and more contorted the resulting magnetic field becomes. A young star, spinning fast and convecting throughout, is a machine perfectly designed to wind its magnetism up to a fever pitch, and this winding is precisely what sets the stage for the flares. So let us follow the chain all the way through. When magnetic field lines are stretched, wound, and braided into ever more strained and contorted shapes, they store energy in their very tension, the way a stretched spring or a twisted rubber band stores energy. The more the field is tangled, the more energy it holds, and the more unstable it becomes. There is a limit to how much strain a magnetic configuration can bear. Push it past that limit, and the field lines, which had been forced into a tortured, high-energy arrangement, suddenly snap into a simpler, lower-energy configuration, reorganizing themselves in an instant. This sudden rearrangement is called magnetic reconnection, and it is the trigger of the flare. When field lines reconnect, all the energy that had been locked up in their strained, twisted geometry is released in a single, catastrophic burst, converted into heat, light, radiation, and the violent acceleration of particles. It is the snapping of the overwound spring, the sudden release of everything the tangled field had been holding back. On our calm modern sun, with its slow spin and its modest, well-organized field, reconnection happens on a comparatively gentle scale, producing the solar flares we occasionally observe. But on a young star, the field is wound far tighter, tangled far more severely, and charged with far more energy. So when reconnection comes, it comes with overwhelming force. The flares of a young T Tauri star are the snapping of a magnetism stretched to extremes by a fast spin and a churning interior, releasing energy on a scale our mature sun simply cannot match. And because the dynamo is constantly rewinding the field, constantly stretching and tangling it anew, the strain rebuilds again and again, so the flares are not rare. The young star reconnects and erupts, rebuilds its strain, and erupts again, a near ceaseless cycle of winding and snapping that keeps the surface in a state of perpetual magnetic violence. This is one of the central ideas of the entire story, so let us state it plainly. Young stars are magnetically violent because they are still churning vigorously throughout their interiors and still spinning rapidly from their birth. The same youth that keeps them swollen and contracting, the same youth that keeps them tethered to a feeding disk, also keeps their internal dynamo running at full, wild power. The fury is, once again, the fury of youth, not of size, not of exotic composition, but of a young star that has not yet calmed its churning interior or slowed its rapid spin. So what does all this magnetism actually do once it boils up out of the depths and breaks through to the surface and beyond? The consequences are spectacular, and they begin with darkness. On the surface of a young star, the magnetic field does not emerge smoothly and evenly. It bursts through in concentrated knots and bundles, places where the field is so intense that it interferes with the normal flow of heat from below. Where a strong bundle of magnetic field punches through the surface, it suppresses the convection in that spot, choking off the upward flow of hot gas. With less heat reaching the surface there, that patch grows cooler than its surroundings, and a cooler patch on a star glows less brightly, appearing dark against the brilliant surface around it. These dark magnetic blemishes are called star spots, and they are the stellar cousins of the sunspots you may have seen on images of our own sun. But here is the difference that matters. On our calm modern sun, sunspots are modest things, small dark freckles that come and go, covering a tiny fraction of the surface. On a young T Tauri star, the star spots are monstrous. They can cover enormous fractions of the star's face, vast dark continents of suppressed magnetism sprawling across the surface, sometimes blanketing a substantial portion of the entire star at once. These giant star spots are not just a curiosity, they are another engine of the variability we have been tracking all along. As the rapidly spinning star turns, these huge dark regions rotate into and out of our view, and because they are so large, they take a real bite out of the star's brightness as they pass. When a great spotted region faces us, the star dims noticeably. As it rotates away and brighter, unspotted surface turns toward us, the star brightens again. So on top of the gusting hotspots from accretion, on top of the uneven feeding, we now have enormous cool star spots wheeling across the face of a fast-spinning star, adding yet another layer to the restless, flickering light. The young star is dark and bright at once, blotched with cool magnetic shadows and blazing accretion impacts. All of it turning, all of it changing, never holding still. But star spots are only the quietest expression of the young star's magnetism. The magnetic field above the surface, the loops and arcs that arch up into the star's atmosphere, store tremendous energy, and that energy does not always stay stored. The magnetic field lines, twisted and tangled by the churning, spinning interior below, become strained and contorted, like rubber bands wound far too tight. And tangled, strained magnetic fields are unstable. They can snap, reconnecting violently into simpler configurations and releasing, in a sudden catastrophic burst, the enormous energy they had been holding. This sudden release is a stellar flare, and on a young T Tauri star, flares reach a scale that beggars comparison with anything our modern sun produces. Our sun does flare. Now and then it unleashes a solar flare, and when one is aimed our way, it can disturb satellites, ripple through power grids, and paint the polar skies with auroras. These events feel dramatic to us. But the flares of a young T Tauri star can dwarf the strongest flares our sun has produced in all of recorded history, releasing energy on a scale that would make our worst solar storms look like sparks. The young star with its supercharged dynamo and its vast reservoirs of tangled magnetic energy, is capable of detonations of light and energy far beyond the gentle temper of the mature sun. These are not occasional curiosities. On an active young star, powerful flares can erupt frequently, again and again, a near-constant barrage of magnetic violence flaring up from the tortured surface. And the flares are not the only weapon in this magnetic arsenal. Above the visible surface of the star lies its outer atmosphere, the corona, a region of thin, extraordinarily hot gas suspended in the star's magnetic field. On a young star, this corona blazes with activity, heated and energized by the relentless magnetism below, and it pours out radiation at the high-energy end of the spectrum, including copious X-rays. A young T Tauri star can be a fierce source of X-rays, far brighter in that high-energy light than our mature sun, its corona crackling with magnetic energy, its surface erupting in flares, the whole outer envelope of the star alive with violence. When astronomers point X-ray telescopes at star-forming regions, the young stars light up like beacons, their fierce coronal activity betraying their youth across the darkness. It is worth picturing what that corona actually looks like, because its architecture is magnetism made visible. The corona is not a simple, smooth shell of hot gas wrapped evenly around the star. It is a structure built and shaped entirely by the magnetic field, a tangle of soaring magnetic loops arcing up from the surface, anchored at both ends in the star, rising high into the atmosphere and curving back down. These coronal loops are like enormous magnetic bridges, and the hot, glowing gas of the corona is trapped within them, flowing along the field lines, suspended above the surface by magnetism. On a young star, with its ferociously strong and tangled field, these loops are larger, denser, and more numerous than anything our calm sun supports, towering over the surface, packed with superheated gas, crackling with energy. The corona of a young T Tauri star is a forest of glowing magnetic arches, and it is within and between these arches that the reconnection happens, that the flares ignite, that the X-rays are born. When we say a young star blazes in X-rays, we are really saying its corona of magnetic loops is so hot and so energetic that it glows fiercely in that high-energy light, a direct readout of the magnetic violence holding it aloft. This raises a fair question. How do we know any of this is real? We cannot fly to a young star and watch its surface. The answer is that the violence announces itself across the spectrum, and astronomers have learned to read those announcements. When telescopes that detect X-rays are pointed at the great star-forming clouds, the young stars within them blaze out where older, quieter stars stay dark, their fierce coronas betraying them at a glance. A nursery full of young stars, dim and unremarkable in ordinary visible light, lights up like a field of beacons when viewed in X-rays, each point a young star with a violently active corona. This is one of the ways astronomers find young stars in the first place, by searching for the X-ray glow of their magnetic fury. The flares announce themselves too. When astronomers monitor young stars over time, watching their brightness night after night, they catch the flares in the act, sudden spikes of light erupting and fading, the unmistakable signature of reconnection releasing its energy. They can measure how often the flares come and how much energy each one unleashes, and the answer confirms the picture we have built. Young stars flare far more frequently and far more powerfully than mature stars, exactly as the supercharged dynamo would predict. The enormous star spots reveal themselves as well, In the regular dimming and brightening of the star as the spots rotate across its face, a rhythm that lets astronomers map how much of the surface the spots cover and how fast the star spins. Every piece of the violence we have described, the spots, the flares, the blazing corona, the X-rays, leaves a trace the telescopes can capture. The raging young star is not a guess. It is a thing we have watched, again and again, written in light across the nurseries of the galaxy. Alongside the flares and the X-rays come the particles. When the magnetic field reconnects and flares erupt, they do not only release light and radiation, they also accelerate charged particles to tremendous speeds, hurling them outward in energetic bursts. The young star flings out blasts of high-energy particles, storms of accelerated matter riding the violence of its flares into the surrounding space. These particle outbursts sweep through the system, through the very disk where planets are trying to form, bathing everything around the star in a harsh, energetic rain. We will see, before we are done, what that rain means for young worlds. For now, simply add it to the portrait. The young star is not just bright and dark and flickering, it is a fountain of high-energy radiation and high-energy particles, a source of fierce X-rays, monstrous flares, and storms of accelerated matter, all driven by the same wild magnetism boiling up from its spinning, churning depths. So we now have a star covered in enormous cool star spots, erupting in flares far beyond anything the modern sun produces, blazing in X-rays from a violently heated corona, and flinging out bursts of energetic particles. And remember, this is the same star we watched earlier pulling matter inward, drinking from its disk through magnetic funnels, glowing with the hot spots of infalling gas. The magnetism does both. It is the single thread that ties together the feeding and the fury, the inflow and the violence. And now we arrive at the most astonishing thing this magnetism can do. The great paradox we have been promising since the very first words of this story. Because the same magnetic machinery that pulls matter in is also capable of throwing matter out. Let us return to that impossible image. A young star drinking a river of gas inward along its magnetic funnels, while simultaneously firing twin jets of matter outward into the dark. How can one object do both at once? How can a star feed and scream at the same time? The answer lies in the deep relationship between the star, its disk, its magnetism, and its spin. And at the heart of that answer is a quantity physicists call angular momentum, the measure of an object's rotation, the spin it carries. Here is the problem the young star faces. It is being fed by its disk, and the material falling in from that disk carries spin with it, adding to the star's rotation. At the same time, the star is already spinning rapidly from its birth. If all of that infalling spin simply piled onto the star with nothing to counter it, the star would spin faster and faster, winding up tighter and tighter, until it began to tear itself apart. Stars cannot spin without limit. There has to be a way to get rid of excess spin, to shed angular momentum, to keep the star from over-rotating as it feeds. And the solution the young star reaches for is to throw matter away. By flinging material outward and carrying spin off with it, the star can rid itself of the excess rotation that feeding would otherwise dump onto it. The outflow is, in part, the star's way of balancing its books, of dumping the spin it cannot afford to keep. The machinery for this is, once again, the magnetic field, working hand in hand with the disk and the star's rotation. The magnetic field lines, anchored in the rapidly spinning star and threading out through the disk and the surrounding gas, act like enormous whirling slings. As the star and the inner disk spin, they drag these field lines around with them, and ionized gas caught on those field lines is flung outward along them, accelerated and channeled by the spinning magnetic structure, hurled away from the star. The magnetic field, in other words, is not only a set of funnels carrying matter down, it is also a set of slings and channels carrying matter up and out, launching gas away from the star and the inner disk along the very same kind of magnetic threads. Feeding and ejection are two faces of one magnetic system, both rooted in the spin of the star and the disk, both shaped by the field lines that bind them together. This outflow takes more than one form, and the distinction matters. Part of it is a broad, continuous stellar wind, a steady streaming of gas away from the young star in all directions, far denser and far more powerful than the gentle wind that drifts off our modern sun. The young star sheds a strong wind, a real river of material flowing outward, carrying mass and spin off into space. But there is also something far more dramatic and far more focused than a broad wind. There are the jets. The jets of a young star are among the most spectacular structures in all of star formation. They are not broad and diffuse like the wind. They are narrow, tightly collimated beams of gas, fired outward from the star in two opposite directions, straight out along the star's poles, perpendicular to the disk. We call them bipolar jets, bipolar meaning two poles, because they fire in two opposing directions at once, one beam shooting out from the top of the system and an answering beam shooting out from the bottom, the disk lying flat between them. Picture the young star at the center, the great disk spread around its equator, and then two thin, brilliant beams of gas blasting straight out from the poles, above and below, racing away into the dark in perfect opposition. The magnetic and rotational machinery of the star and inner disk acts like a pair of cosmic cannons aimed at the heavens, focusing the outflow into these narrow, opposing beams and firing them outward at tremendous speed, hundreds of kilometers per second, the same staggering velocities we saw in the infall, but now pointed the other way. And these jets do not vanish quietly into space. They tear outward through the gas surrounding the young star, and where the fast-moving jet slams into the slower material around it, it creates violent shock fronts, regions where the collision heats and lights up the gas, making it glow. These glowing knots and arcs, lit up where the jets crash into their surroundings, are visible structures, real beacons of the outflow that astronomers can see and study. They are called Herbig-Haro objects, named for two astronomers who studied them, and they appear as bright little clumps and streamers of glowing gas strung out along the path of the jet, far from the star itself, marking where the beam has ploughed into the surrounding cloud. These HH objects are like the muzzle flashes and impact marks of the star's twin cannons, glowing evidence written across the nebula of the matter the young star is hurling away. When you see images of a young star with two thin glowing beams shooting out from its poles, ending in bright knots far out in the surrounding gas, you are seeing this whole magnificent process made visible. The jets and their shocks, the outflow of a star that is throwing matter into the void. Now hold both halves of the picture together at once, because this is the heart of everything. At its equator, the young star is pulling matter inward, drinking from its disk along magnetic funnels, the infalling gas slamming onto its surface in blazing hotspots. At its poles, that same star is firing matter outward, launching a strong wind and two narrow, opposing jets straight out into space, shedding spin and mass into the dark. The star is feeding and ejecting simultaneously, drinking at the waist and screaming at the crown, and there is no contradiction in this once you understand the machinery. It is all one connected system, the disk feeding the star's spin and magnetism flinging excess matter and rotation back out, the inflow at the equator and the outflow at the poles bound together by the same magnetic threads and the same relentless spin. The young star is not confused. It is balancing. It takes in matter to grow and throws out matter to keep from spinning itself apart. And in doing both at once, it produces one of the most extraordinary spectacles in the cosmos. A single object pulling in and pushing out, feeding and firing, all at the same time. This is what we glimpsed in the very first words of this story. The monster sun that fed and screamed at once. And now we understand it. The young star rages because it is still churning vigorously inside, still spinning rapidly, still magnetically wild, and still locked in a fierce exchange of matter and motion with the disk around it. Its star spots are vast because its dynamo is fierce. Its flares are monstrous because its tangled fields store enormous energy. Its corona blazes in X-rays and its particle storms sweep the system because its magnetism is relentless, and its jets fire matter across light years because the only way to keep feeding without overspinning is to throw the excess back out into the dark. Every piece of the violence traces back to the same source, a young star that has not yet calmed its interior, slowed its spin, or let go of its disk. But we have been speaking as though every young star behaves the same way, as though they all carry thick disks, all feed fiercely, all fire identical jets. That is not true. And the differences between young stars turn out to matter a great deal. Some of these stars are still wrapped in heavy disks, drinking greedily, blazing with accretion and emission. Others have already lost most of their disks. Their feeding faded, their jets gone quiet, even as their magnetic activity still simmers. The youth of a star is not one fixed condition, but a changing one. A phase that evolves as the disk drains away and the feeding declines. And those differences, between the still feeding and the nearly finished, between one kind of young star and another, are where we turn next. Along with the deepest question of all, what this raging youth meant for our own sun, and for the worlds, including ours, that were trying to form in the storm. We have been speaking as though every young star rages in the same way, wrapped in the same thick disk, drinking the same fierce river of matter, firing the same brilliant twin jets. But that picture is too simple, and the differences between young stars turn out to be one of the most important parts of the whole story. A T Tauri star is not a single fixed kind of object. It is a star caught in a stage, and like any stage, it has a beginning, a middle, and an end. A young star early in this phase, still buried in material, still feeding greedily, behaves very differently from one near the end of the phase, its disk nearly gone, its feeding faded to almost nothing. To understand stellar youth properly, we have to recognize that it changes, that the violence rises and falls across the millions of years the phase endures, and that at any given moment, the galaxy holds young stars at every point along that road. So let us draw the great dividing line that astronomers use to split these stars into two families, because that line tells us almost everything about how a young star ages. On one side stand the classical T Tauri stars. These are the young stars we have been describing throughout this entire story. The ones still surrounded by thick, substantial disks, still actively feeding, still drinking matter through their magnetic funnels and glowing with the hotspots of accretion. A classical T Tauri star is a star in the full fury of its feeding youth. Because it is still pulling in a strong river of gas, it shows all the signatures of that feeding written boldly in its light. It blazes with excess ultraviolet from its accretion hotspots. It pours out strong emission lines, particular bright features in its light produced by the hot, fast-moving, infalling gas, features so prominent they became one of the chief ways astronomers identify these stars in the first place. It often drives powerful winds and jets, flinging matter outward even as it drinks inward. The classical T Tauri star is the feeding star, the connected star, the one still locked in fierce exchange with a disk that has plenty left to give. When you picture the raging young sun from the opening of the story, you are picturing a classical T Tauri star. On the other side stand the weak-lined T Tauri stars, and the name itself tells you what has changed. The lines, those bright emission features produced by feeding, are weak. They have faded. And they have faded because the feeding itself has faded. A weak-lined T Tauri star is a young star that has lost most or all of its disk, or at least lost the thick inner disk that supplied the funnels. With little or no material left to drink, the accretion has dwindled to a trickle or stopped altogether. The hotspots have cooled, the excess ultraviolet has dimmed, the jets and the strong winds have quieted. The great river of matter that defined the star's feeding youth has run dry. This is a young star that has, in a sense, finished one part of growing up, the part that depended on the disk, even though it has not yet reached full maturity. But here is the crucial subtlety, and it is easy to miss. A weak-lined T Tauri star is not a calm star. It has lost its disk and its feeding, but it has not lost its ferocious magnetism. The internal dynamo, born of churning convection and rapid rotation, is still running at full power, because the star is still young, still spinning fast, still convecting vigorously throughout its interior. So a weak-lined T Tauri star still erupts in monstrous flares. It still blazes in X-rays from a violently active corona. It is still covered in enormous star spots that wheel across its face as it spins, still flinging out bursts of energetic particles. All the magnetic violence we explored remains, undiminished. What has changed is only the feeding. The disk-related drama, the accretion hotspots, the excess ultraviolet, the strong emission lines, the jets, all of that has faded with the disk. But the dynamo-driven drama, the spots and flares and X-rays and particle storms, rages on. The weak-lined star has simply shed the half of its violence that came from the disk, while keeping the half that comes from within. This distinction reveals something profound about how a young star ages. The two great engines of its violence, the feeding from the disk and the magnetism from the dynamo, do not switch off at the same time. The disk-driven violence fades first, as the disk drains away over a few million years. The dynamo-driven violence persists far longer, fading only slowly as the star, across tens of millions of years and beyond, gradually slows its spin and settles its interior on the long road to maturity. So the journey from classical to weak-lined T Tauri star is the journey of a star losing its disk and its feeding while still carrying its inner magnetic fury. And the further journey beyond the weak-lined stage into true main sequence adulthood is the much slower journey of the dynamo itself winding down, the spin slowing, the flares calming, the spots shrinking, the star at last becoming the steady, reliable furnace we recognize. The calm of our modern sun is the end of both journeys. The disk long gone and the dynamo long since tamed. There is a deeper puzzle hidden inside this slow calming of the dynamo, and it returns us to the question of spin, which sits at the very heart of why these stars rage. We have said that a young star spins fast, inheriting its rotation from the collapsing cloud that formed it, and that this rapid spin is half the reason its dynamo is so fierce. But here is the difficulty. A young star is also being fed, and the matter raining down from the disk carries spin with it, dumping still more rotation onto the star. Feeding should make the star spin faster and faster over time, and yet, when astronomers measure the spin rates of young stars still wrapped in thick, feeding disks, they find something surprising. Many of these stars are not spinning faster and faster at all. They are holding a remarkably steady, even slow, rotation, despite being fed a constant stream of spin-laden matter. Something is holding their spin in check. Something is bleeding away the rotation as fast as the disk delivers it. That something appears to be the disk itself, working through the magnetic threads that bind it to the star. The same magnetic field lines that connect the star to its disk act like a kind of leash or clutch between the two. And through that magnetic connection, spin can be transferred back and forth. When the arrangement is right, the disk drags on the star through these magnetic threads, siphoning off rotation, carrying spin outward into the disk and out through the wind and jets, holding the star's spin steady even as feeding tries to wind it up. Astronomers call this disk locking or disk breaking, the idea that a young star's spin is regulated, held in check, by its magnetic embrace with the disk around it. The star is leashed to its own disk, and that leash keeps it from spinning itself apart. Now follow what happens when the disk drains away. Once the disk is gone, the leash is cut. The magnetic braking that held the star's spin in check disappears, and at the same time, the star is still slowly contracting, still shrinking inward. And just as the collapsing cloud sped up as it shrank, a contracting star spins faster as it pulls itself in. So a young star that has lost its disk can actually spin up for a time, turning faster as it contracts toward maturity, its dynamo still fierce. Only over far longer stretches of time, across tens of millions of years and beyond, does the star finally begin to shed its spin for good, slowed at last by its own wind carrying rotation away into space. This long, gradual spin down is the true road to calm. As the star slowly loses its rotation over its early life, its dynamo weakens, its flares subside, its spots shrink, and the magnetic fury of youth fades by degrees. The calm of our modern sun is, in the deepest sense, the calm of a star that finally slowed down. The fury was the fury of fast rotation, and maturity is what arrives when the spinning, at long last, winds down. So the loss of the disk and the decline of accretion are not minor events. They mark a turning point in the star's behavior, the moment when one of its two great sources of violence falls silent. A young star early in the T Tauri phase is a classical star, disk-wrapped and feeding and firing. A young star later in the phase, its disk consumed by accretion and planet formation and blasted away by its own radiation and winds, becomes a weak-lined star, no longer feeding but still magnetically wild. And eventually even that wildness fades, and the star crosses onto the main sequence to begin its long, quiet, adult life. We must never imagine then that all young stars look alike. Some are still drowning in disks, others nearly stripped bare, and the violence each one shows depends on exactly where it stands along this changing road. Now that we understand what a T Tauri star is and how it changes, we must be careful to separate it from several other objects with which it is easily confused, because the distinctions sharpen our understanding of exactly what makes this stage unique. There are three neighbors a T Tauri star is often mistaken for, and each comparison teaches us something. The first is the protostar, the stage that comes just before. It is tempting to lump these together, to imagine that a T Tauri star is simply another name for a protostar, but that would be a serious error, and it is worth being precise about why. A protostar is the earlier, more deeply hidden stage, the glowing core still buried within the thick envelope of gas and dust from which it is forming, still gathering the bulk of its mass, often invisible to ordinary light and detectable mainly in the infrared that leaks through its cocoon. The protostar is still being built, still wrapped in the dense shroud of its birth. A T Tauri star, by contrast, has emerged. It has shrugged off most of that envelope and become a distinct, visible star, surrounded now by a thinner disk rather than a thick, obscuring cocoon. The protostar is the buried beginning. The T Tauri star is what steps out of the shroud afterward. Recognizable, visible, but still young and unsettled. One is hidden and still assembling its mass in bulk. The other has appeared and is refining itself toward maturity. They are consecutive chapters, not the same chapter under two names. The second neighbor sits at the far end of the road, the mature red dwarf or yellow dwarf, the settled low-mass star living its long main sequence life. Our sun is a yellow dwarf. The most common stars in the galaxy are red dwarfs, smaller and cooler. It might seem that a T Tauri star is just a young version of these, and in a sense it is. But the differences in behavior are enormous, and they all trace back to the differences we have explored. The mature dwarf has finished contracting. It has reached its compact, stable size. It is powered by steady, regulated hydrogen fusion in its core, the great furnace fully lit. It has lost its disk entirely and feeds on nothing. Its spin has slowed and its dynamo has calmed. So its magnetic violence, while not always zero, is mild and manageable compared to its youth. The T Tauri star is the opposite on every count. It is still swollen and contracting, not yet settled. It shines largely on gravitational contraction, not on dominant core fusion. It may still carry a disk and still feed. It spins fast and rages magnetically. The mature dwarf and the T Tauri star can have exactly the same mass, can even be destined to become the very same kind of star, and yet they behave like utterly different objects, because one is at the calm end of life and the other is in the storm of its youth. The third neighbor is the one that lies not before or after the T Tauri star, but in a sense, above it, the more massive young stars known as the Herbig AE-BE stars. These are the higher mass cousins of the T Tauri stars. Young pre-main sequence stars like them, also still surrounded by disks, also still settling toward maturity, but built on a grander and heavier scale. Where a T Tauri star is a young low-mass star, around the mass of the Sun or below, a Herbig AE-BE star is a young intermediate mass star, heavier and hotter. The youthful version of stars more massive than the Sun. They share the broad theme of stellar youth, the disk, the pre-main sequence status, the unsettledness, but they differ in important ways tied to their greater mass. Their interiors are structured differently. with less of the deep, full-bodied convection that drives the fierce dynamos of the low-mass T Tauri stars. So the source and character of their magnetic activity is not the same. The key point is one of scale and mass. The T Tauri stars are the young, low-mass stars, the youthful suns. The Herbig AE/BE stars are their heavier siblings. And this distinction lets us correct a tempting but wrong idea. The violence of a T Tauri star does not come from it being especially massive. Quite the opposite. These are modest, low-mass stars, and their fury is the fury of youth, not of heft. The heavier young stars are a separate class with their own behavior. The raging young sun of our story is firmly a low-mass T Tauri star. Violent not because it is big, but because it is young. With all these distinctions in place, we can finally turn to the question that has been waiting beneath this entire story. The question that gives it weight and makes it personal. What does this raging youth mean for the planets trying to form in the storm, and what did it mean for our own world? Remember where the planets are forming. They are forming in the disk, the very disk that feeds the star. The flat spinning plate of gas and dust wheeling around the young star's equator. And that disk does not sit in a peaceful place. It sits bathed in everything the young star throws at it. The intense ultraviolet light from the accretion hotspots. The fierce X-rays from the blazing corona. The monstrous flares erupting again and again from the tortured surface. The storms of energetic particles flung outward by the magnetic violence, the strong winds streaming off the star, the forming planets and the gas and dust that will become them are growing up inside a storm, soaked in radiation and swept by particle blasts and stellar wind, all of it pouring out of the young star at the center of their world. This storm shapes the planets in profound ways. Consider the intense radiation, the flood of ultraviolet light and X-rays pouring off the young star heats the disk and can drive material off it entirely, especially from the outer reaches where the star's gravity holds the gas only loosely. This radiation-driven stripping is one of the very processes that, over millions of years, helps clear the disk away, ending the feeding phase and bringing the classical T Tauri star toward its weak-lined future. So the star's own violence helps dismantle the disk from which its planets are forming, setting a clock on how long the raw material of worlds remains available. Planets must form before the storm strips the disk bare, racing against the very star that lights them. The storm shapes not only how long the planets have to form, but where and what kind of worlds can form at all. Recall the snow line, that boundary in the disk where the temperature drops low enough for ice to remain frozen. Its position is set by the heat of the young star, and a raging, oversized, brightly burning young star pushes that boundary outward, governing where in the disk ice can join rock as a building material. Inside the line, the warm inner disk yields small, dense, rocky bodies. Outside it, the cold outer disk, enriched with ice, can build far larger worlds. The violence of the young star, its size and brightness, and the radiation pouring off it, helps draw the very map of where rocky planets and giant planets will take shape. The storm is not just a hazard to planet formation, it is one of the forces that organizes it. And the building itself is a delicate, competitive process unfolding under that storm. Planets do not appear fully formed. They grow by stages. As dust grains collide and stick into pebbles, pebbles gather into boulders, and boulders assemble into mountain-sized bodies called planetesimals. The true seeds of worlds, which then collide and merge into ever larger planets. Every stage of this slow assembly is happening inside the disk, soaked in the young star's radiation, swept by its particle storms and winds, the fragile clumps of new matter taking shape amid a constant barrage of energy. The energetic radiation can heat and stir the disk, influencing how the dust settles and clumps. The relentless winds and blasts help disperse the gas the giant planets need. The forming worlds are not assembling in peace. They're being built in the middle of a storm, by a star that is simultaneously providing their raw materials and trying to blow those materials away. That the planets form at all, that worlds like ours emerge intact from such violence, is a quiet marvel written into the youth of every sun. Now consider the young atmospheres of the planets themselves. A forming world that has managed to gather an atmosphere, an envelope of gas around a growing rocky core, finds that atmosphere under relentless assault. The intense ultraviolet and X-ray radiation from the young star heats the upper layers of a planet's atmosphere, puffing them up and driving them off into space, stripping gas away from the top. The storms of energetic particles and the strong stellar wind batter the atmosphere as well, eroding it, carrying it off. A young planet orbiting a raging T Tauri star is fighting to hold onto its air against a star that is actively trying to tear it away. The atmospheres the planets ultimately keep, and the atmospheres they lose, are shaped in part by how fiercely their young star raged, and how close they orbited to that fury. The violence of stellar youth is not a distant backdrop to planet formation. It is an active force, sculpting the disks, setting the timetable for building worlds, and stripping the young atmospheres of the very planets, taking shape in its glare. And this brings us, at last, all the way home to our own sun and our own world. Because everything we have described almost certainly happened here. 4.6 billion years ago, our sun was a young star, and there is every reason to believe it passed through exactly this T Tauri phase. It was once swollen and contracting, shining on the energy of its own collapse before stable hydrogen fusion took over as its dominant engine. It was once wrapped in a protoplanetary disk, the very disk from which the Earth and all the other planets of our solar system formed. It once spun far faster than it does today and churned vigorously throughout its interior, driving a ferocious dynamo. It was once covered in enormous star spots, erupting in flares far beyond anything it produces now, blazing in X-rays, flinging out storms of energetic particles. And it very likely drove a powerful young wind, the so-called T Tauri wind, streaming off the young sun far more strongly than the gentle solar wind we know today. That young sun's violence may have left its fingerprints all over the solar system we live in. The strong T Tauri wind of the young sun, streaming outward at the height of its feeding youth, may have helped sweep the early solar system clean, blowing away the leftover gas and dust that lingered after the planets had formed, clearing the disk, ending the era of building. The intense radiation and particle storms of the young sun would have soaked the forming planets, helping to shape which worlds kept thick atmospheres and which were stripped, helping to determine the difference between a world that held its air and a world that lost it to space. The young sun's fury was not gentle to the worlds forming around it, and the solar system we know, with its particular arrangement of planets and atmospheres and cleared out spaces, bears the marks of a star that was once as wild as the faint flicker in the constellation of the Bull. Think about what that means as you stand under the modern sun. The steady golden disk that warms your face, the the very symbol of constancy across every human culture, was once a raging young star. It was swollen and flickering, dark with monstrous spots and bright with accretion impacts, erupting in flares, blazing in X-rays, drinking matter from a disk along magnetic funnels, while firing wind and perhaps jets out into the dark. The calm you take for granted was earned across millions of years of violence. The reliability you build your life around is the end state of a turbulent adolescence that shaped the very ground beneath your feet. The earth itself formed in that storm, in the disk around that raging young sun, and the fact that you are here at all is, in part, a consequence of how that violence played out, what it stripped away and what it left behind. And this is why the young stars scattered across the galaxy matter so much to us. When we look at the faint flicker of T Tauri in the constellation of the Bull, or at the young stars strewn through the great star-forming clouds, we are not looking at alien curiosities with nothing to do with our world. We are looking at living portraits of our own sun's lost youth. We cannot travel back 4.6 billion years to watch the young sun rage, but the galaxy has preserved the spectacle for us, frozen in the act all across the sky, in thousands of young stars caught at every stage of the same journey our sun once travelled. Each one is a window into a chapter of our own origin story. A chapter that ended long before there was anyone here to witness it. To study T Tauri stars is, in a real sense, to study our own beginning. So let us gather the whole story together. Now that we have followed it from the swollen contracting star to the feeding disk, to the magnetic fury, to the worlds forming in the storm. A T Tauri star is a young, low-mass, pre-main sequence star, caught in the long unstable transition between the buried protostar and the settled main sequence adult. It has not yet made stable hydrogen fusion its dominant engine. Instead, it shines largely on the energy of its own gravitational contraction, slowly shrinking from its swollen youthful size toward its compact mature form, which is why it can be larger and brighter and far more variable than the star it will become. It is wrapped, at least at first, in a protoplanetary disk, and it feeds on that disk through magnetospheric accretion, its powerful magnetic field carving a hole in the inner disk and funneling ionized gas down along curving field lines to slam onto the surface at hundreds of kilometers per second, creating blazing hotspots that glow in excess ultraviolet and flicker as the feeding gusts and the star spins. That same powerful magnetism, born of vigorous convection and rapid rotation driving a ferocious dynamo, covers the star in enormous star spots, erupts in monstrous flares, blazes in X-rays from a violently active corona, and flings out storms of energetic particles. And the magnetism does one more astonishing thing. It throws matter outward even as the star drinks matter inward, shedding excess spin through a strong stellar wind and through narrow bipolar jets that fire straight out along the poles at tremendous speed, lighting up glowing shock fronts where they crash into the surrounding gas. The star feeds at its equator and screams at its poles, pulling in and pushing out at once, balancing the matter and the spin it exchanges with the disk around it. Young stars are violent then, for one deep and unified reason. They are still assembling, still shrinking, still spinning fast, still churning vigorously inside, and still locked in a fierce exchange of matter and motion with their disks. The fury is the fury of youth, not of size, not of exotic nature, but of a star that has not yet calmed its interior, slowed its spin, lost its disk, or lit its core furnace as its steady engine. And we must never flatten all of them into one image, for they differ. The classical T Tauri stars still drink from thick disks and blaze with feeding. The weak line T Tauri stars have lost their disks and their feeding, but still rage magnetically from within. The phase changes as the disk drains and the spin slows, and at any moment the galaxy holds young stars at every point along that road, no two quite alike. This is the chapter of stellar life that our own sun once lived, the violent adolescence that shaped the disk from which our planets formed, that swept the early solar system clean, that helped decide which worlds kept their air and which lost it. The next time you feel the warmth of the sun on a quiet afternoon and think of it as the calmest, most dependable thing in your life, remember that it was not always so. Remember that it was once a raging young star, swollen and flickering, dark with spots and bright with flares, feeding and screaming at once. The calm was earned. The storm came first. And out of that storm came the disk, and the worlds, and eventually the world beneath your feet, and you, looking up at the steady star that was once as wild as any in the sky,